So when you get the creation of a transverse wave, so whether it's a radio broadcast or the light coming from the sun, all of that's on the EM spectrum. All of that is what's called a transverse wave. And a transverse wave can travel, can vibrate perpendicular to its path in any plane. And so what that means is this: if the direction of the wave is that way, like what I'm trying to draw is like into the page, you can have light that goes like this, up and down along that line, or you can have it so that it goes this side and this side. You can get all these angles, and you can have any angle in between. And in fact, when light does get created, depending on the source it gets created from, it's going to be a mess. The light signal we get, especially from the sun, created by the fusion of hydrogen, helium, and all those other heavier elements in the sun, is messy. And so if you were to look at it right up, like straight on, i.e., here's the sun, and you're looking directly at it, and the light's coming directly at you, what that transverse wave is doing, you could get some that look like this, where the wave is bouncing left and right, some that look like this, where the wave is bouncing angled that way, some where the light is bouncing up and down, and it's all of these patterns are going to be within the stream of light approaching you, and it's going to be kind of a jumbled mess. Which is great. It's the way it is. Nature benefits from it. But there are ways to eliminate certain patterns that show up here. When light waves can vibrate in all planes, we call this non-polarized light. We can polarize light though, relatively easily. In order to polarize light, we need to pass through what's called a polarizer. Hands up if you've ever owned a pair of polarized sunglasses. Has anyone ever gone out and bought polarized sunglasses? Often they're slightly more expensive than your regular sunglasses because extra work goes in. Really? None of you have? Okay. Extra work goes into building those lenses because they're not just shaded. On sunglasses that aren't polarized, there's films put over top to make everything darker. In a polarizer, extra work has gone on into building that glass. So not only is it maybe tinted a little bit darker, but how a polarizer works is this. You can have a polarizer that has a whole bunch of vertical slits. Like with a pair of sunglasses, if all of those slits are in the same direction and they're all really fine, you can look through them no problem. An example of a polarizer would be one of these. I need two of these over here. These are polarized. Polarizers. When you just have one of them, like this, there is really no difference between looking at this piece of plastic, and you could assume that it's tinted, like a pair of sunglasses could be tinted, but it's not just tinted, and I'll show you how we know that. It's not just tinted, but it does make things darker. You can still see through it. Light is still making its way through, but trust me when I say this is a polarized piece of plastic. I'll show you what I mean by that in a second. When you have a polarizer and it interacts with light that is polarized in all sorts of directions. So if I have my beam of light coming this way, and along that beam of light, I have light that's going left and right. The waves are moving left and right. I have waves that are moving at an angle, waves that are moving at an angle, waves that are moving up and down. When they hit the polarizing grate, what the polarizing grate does is it blocks all of the waves that are moving in any direction other than what the polarizer is producing. So when this beam of light that's coming in, moving in all sorts of different directions, hits this vertical polarizer, what gets created as it's going through is light that is polarized in a specific direction. In this case, the light is being polarized vertically. It blocks all of these other directions, and this is what comes out the other end. So this isn't just a tint. You're going to ask me, how do you know? Can you prove? Yes, I can prove. I will show you how I know. So my next question is going to be, and I should have drawn this a little bit lower, if I throw another polarizer over here, and after I've polarized it vertically, I put some slits. So my polarizer is now a horizontal polarizer. If I have previously polarized my light so that it is only vertical, and I try and send it through one of these, what's going to happen? What would you expect to happen? This light's going to get blocked now, and there's going to be nothing coming out the other end. So the way to tell if, in fact, you have polarizers is by doing exactly this. If you want to buy, and my dad first showed me this when I was roughly your age, polarized lenses are really good when you have situations where light is being reflected, and when light is reflected, it messes with the polarization. And you want to eliminate some of that polarization. For example, if you're a skier, having polarized ski goggles can cut the light bouncing off the snow. If you fish, having polarized lenses can cut the glare from the surface of the water, allows you to see what's underneath. So a way to tell whether or not things are polarized is by doing this. You can see through it. There's another polarizer. You can still see through it. But if I take these two polarizers and I turn them perpendicular to each other, what should happen? Like that. You see nothing. And it has nothing to do with the fact that they're both tinted. Because yeah, they're both tinted. Yeah, you can see through them. Tell me you can see through them. Yes, you can see through them. I can see it on my video. But if I take these things and as I rotate them, now no light gets through. Because these polarizers are now perpendicular to each other. And so if you want to buy sunglasses and they claim to be polarized, this is all you have to do to test. You take your two sunglasses that both claim to be polarized, put them perpendicular to each other, and if they don't block out everything, if I remove him, he's back. If I put him, he's back. Put them on top of each other, you got nothing. Those things are not polarized unless they can do this. Yes, sir. Sorry? So this is diagonal. This is the same diagonal. Now it's black. As long as it doesn't matter which way they're rotated, as long as they're perpendicular to each other, you're still going to get that same effect. So Vian, actually, no, I have a bunch of these. Take them out, play with them. Pass them around. And it's not just up, down, left, and right that you can polarize them. You can polarize things, you can circularly polarize light so that what's coming out the other end is actually a spiral of electromagnetic wave. It doesn't look any different to you guys as you experience things. The only place it shows up and is a little bit weird is when you start to take multiple polarizers and stack them on top of each other. Because one polarizer by itself isn't going to look anything different other than tinted. But it's not. Is this what I wanted to show you guys? Yes, this is what I want to show you guys. So here's an example of where this could be useful. I'll make this bigger. Yes, computer, figure yourself out. I believe in you. Okay. All these cool videos come from Florida. So this is your average waterway in Florida. As you can, this is what water would look like unpolarized. You're just walking by the bank, maybe. Yeah, of course there is. It's Florida. Of course it's gonna be an alligator. You put your polarized lenses on top. All of a sudden you now have that. You couldn't see it before because of the light bouncing off. Unpolarized, all you're gonna see is the reflection of the light. If you're able to eliminate a whole ton of that light, now all of a sudden you can see what's bouncing off the bottom. That is not an insignificant creature. And again, because as soon as I said Florida, yeah, Lena, you're right. It's going to be an alligator. Now you can see what's actually in there. Doesn't have to be Florida, it could be Australia, but yeah. It's creatures like this that pop out at you. So when two polarizers, and I'll make a note of this here. When two polarizers are at 90 degrees, no light will pass through. Now, you cannot polarize sound. Sound's a longitudinal wave. It's vibrating back and forth. Hands up if you've ever been to a 3D movie. So 3D movies work the same way. Flip the page. We already talked about this top line. It's on the previous page. Don't worry about it. Much of the glare reflected from a horizontal surface, like the surface of water, is polarized horizontally. So light comes in, it's a bit of a mess. That flat surface functions as a polarizer, and most of it comes at you horizontally polarized. If you can get some polarized sunglasses, these can be used to reduce the glare. Those polarized lenses are almost always going to be vertical. And what that's going to do is it's going to cut away a lot of the light bouncing off the surface and is going to allow you to see the light that's bouncing off the bottom. 3D movies work similarly. Older style 3D movies used polarization to give that appearance of depth. You'd have light that was polarized in different directions, so the light from the projector would come out different. Depending on what you wanted to see, whether it was your left eye or your right eye, the left eye picture would be overlaid on the right eye picture, and it'd be polarized differently. So maybe one would be polarized up and down. The left eye would be polarized up and down. The right eye would be polarized left and right. It bounces off the screen. It gains that mixture back once it reflects off of a surface. But then when it hits those glasses, those lenses can or will block out the light you don't want from the eye you don't want it to see, and then the opposite on the other, and you get this idea of depth. The left and right eye are filmed or being projected at different depths, and then the left and right come back to you at different depths, and your brain then reconstructs that as a single image with depth. And that's how 3D movies work. There are companies that are bringing this technology to modern televisions, where instead of having something like picture-in-picture, they have a television that's actually emitting two different pictures overlaid on top of each other. And you can buy glasses so that one set of glasses will block out one polarization. the other set of glasses will block out the other polarization. So if you and your significant other, for example, wanted to watch two different TV shows, you can do that side by side. You just set the two channels you want your TV to produce. It'll produce one channel in one polarization, the other channel in the other polarization, laid directly on top of each other. One set of glasses will see one picture, the other set of glasses will see the other picture, because the polarization will be cut out from the screen you don't want to see, or the picture you don't want to see. Obviously, the sound's another issue. Now you bring earbuds into this, but you can still sit side by side watching the same large television with your significant other, just watching different pictures. It's weird and pretty cool. So polarization is just another one of these effects that shows up in waves. A whole bunch of these standalone things. Yes, you bet. Okay, flip the page. Refraction. Refraction is the last, well, it's not true. It might be true, depending on how far we get through it, because reflection is really cool too, but we already got and talked about reflection. Refraction is the last big wave phenomenon that we're going to talk about here in this chapter. And here's how refraction works. When you have a wave traveling, so the example here is I have water waves, and when water waves, or when any wave, as it's traveling, as a wave encounters a different medium, depending on the properties of the medium you're encountering, your wave is going to change. So in this particular example, we've got deep water, and in deep water, water waves are allowed to propagate very, very quickly. They're allowed to move super fast, so that's, and the big example is with a tsunami. If you have an earthquake underwater, produces a tsunami, that water, or the energy, the wave in deep water, will travel at roughly the speed of a 747 jet at cruising altitude. Very, very quickly. It'll pass through and past you so fast you might not even recognize that you just survived a tsunami. If you're sitting on the water in deep water, or you're scuba diving at depth, you may never know that it would even hit you. It'll pass through you so fast, with a fairly large wavelength. But as that wave, the water wave, reaches shallow water, it starts to back up. It's being blocked a little bit by the shallowness of the land. And what you get is this effect where, as the wave interacts with that shallower water, it slows down. And the wavelength actually decreases. In water waves, as it slows down, that energy still has to go somewhere. It slows down, the wavelength decreases. So in a tsunami, where does the water go? What do you know about tsunamis? Up. Exactly, up. The amplitude increases. So in water waves, when you have this effect happening, amplitude increases. Wave gets tall, which is why tsunamis are so devastating. If you experience a tsunami in the middle of the ocean, there's an earthquake on Vancouver Island, and you're on a boat halfway to Hawaii, you're never going to experience it. The Hawaiians will when it gets to them, but you won't. And this is what refraction looks like. The waves will bend as they start to experience the shallower water. Wavelength will decrease, and then the water amplitude will increase. Light behaves a little bit differently. The frequency doesn't necessarily, if going back to this, the frequency doesn't necessarily change because the waves were generated in deep water. The wavelength, however, does. As the depth increases, so does the wavelength. And since v equals lambda f, the velocity of, because frequency changes and the wavelength goes down, the velocity of the wave decreases as well. So in water waves, you get these slower, taller waves. When you're ready, flip the page. In light, the effect is a little bit different. And instead of talking about deep versus shallow, in light, the effect happens when you enter a new medium. So for example, you're in air and you enter water, and the barrier between them is just the surface. Let me grab another color. This is harder to see. This is just the surface of the water, or the barrier between these two media. You get this effect where, I'll see if I can demonstrate it using this. It sort of worked at lunchtime. Let's do this. There. Can you see what I'm looking at here? You guys see the line, the vertical line all the way down? You get this effect where as you shine light in, go back here. What happens? What does that mean? As I shine my light, what does refraction mean? It's changing direction. It's bending. It's not super easy to see there. It's easier to see on this one. I want it that. Yeah, let's look like that. As my light comes in, you can see it's coming in straight here. As it hits the surface of this plastic block, it bends in towards that line on the inside. And you can actually, can you see it bending around, bouncing around? Yeah, you get a portion of it where it's bouncing down this way and bouncing back. Does it bounce back out? Where are we here? If I shine it that way. Yeah, there it is. It's hitting here. Look at the wall behind here, Day. Here, Day, look at the wall behind you. You get a portion of it where it's bouncing off that way, but you can also see it coming in this way, and another portion of it is over here on this side of the class. So when you have light that encounters the change in, I'm done here, Day, a change in media, you get this effect called refraction where the light actually begins to bend. And here's how it does that. So we got light coming in. Light bounces in. We call that our angle of incidence. It's always measured from the vertical. That's why I had those pencil markings all over the page, perpendicular to the various surfaces. And as the light experiences the boundary, it's going to bend. And the way it bends is towards that normal line when, and so in theta, in this case, theta I is bigger than theta R when you have a medium that has what's called a higher index of refraction. So as it goes from a low index of refraction to a higher index of refraction, you get this bend where it bends towards this line. How much light bends is determined by the substance it's moving into. The measure of how much light will bend in a substance is called the index of refraction, and I have tables of this for you. Air has an index of refraction of basically 1. It's not exactly 1, but it's effectively 1. It's actually 1.6 0.00029, which, as far as our math is concerned, may as well be 1. Vacuum has an n equals 1. So as far as light is concerned, air and a vacuum are effectively the same. It's not completely true, but for our purposes in this classroom, it'll work. If n is more than 1, the substance bends light more than air does. If it's less than 1, the substance bends light less than air. And a larger n will give you more bend. And here's an application of some of this stuff. Because light bends, when you're looking at something underwater, for example, the actual object may be here. So light comes in, it bounces off the object underwater. Could be a fish, could be a model submarine, don't know what it is. It bounces off, and when it hits this barrier, because it's going from a substance of higher index of refraction to lower, it bends away from this normal. And so then it bends and travels to your eye. But your brain doesn't know how to take into effect this bend. It doesn't necessarily know what these substances are. Your brain's not going to do the math. And so as far as you're concerned, because the light's coming at you at this direction, what you see is the image of the object as if it were over here. So you actually, if you're looking at an object in water, you actually see an object that's shallower than it actually is. And the further you are away horizontally, the greater this effect is. If you're directly on, so if you look here, or if you put this together, this is the normal line. For a light that comes in vertically on the normal, it's not going to bend at all. It's going to go straight down and come straight back. So if you were directly above this object, you'd see it exactly where it is. But as soon as you start to move horizontally away, you're going to start to get this effect where you perceive it to be in a different location than it actually is. And the further you're over, the further away you're going to perceive the image to be. So an example of an application of this would be something like spearfishing. Whether it's you or, for example, a heron. My family and I went and walked around Wilban Park yesterday. We saw a few of them. Herons are spearfishing birds. They have long beaks. Their goal is to get up high and above as much as possible to their prey, so that if they can get directly above it, they're going to hit it exactly where it is every time. But if you see it from an angle, if you're trying to spearfish for this object, for this fish, and you aim here, you're not going to hit it. But if you aim below where the image you're perceiving actually is, you will actually spearfish your fish. And with practice, you can get a handle on how best to do this. It's a neat effect. Flip the page. When waves or light pass from one medium to another, the direction, speed, and wavelength all change. The frequency does not. So when light passes from a medium that has a low index of refraction to a substance that has a higher one, the light slows down and bends towards the normal. So low index of refraction would be something like air. I'll show you the table of all these indices of refraction in a second. Higher indexes of refractions are things like water or gems. You get this bending. When light passes from a medium that has a high index of refraction to a substance that has a lower index of refraction, the light speeds up and bends away from the normal. So for example, the light's in glass, leaving the glass, going to air, you're going to get this bend. If you extend this idea, so here I'll put some values in here. Ni is greater than 1. Here, NR is equal to 1. So greater to lower, you get this kind of bend. If we extend this idea and start to decrease this incoming angle, as you decrease it further and further, this one's going to bend further and further away from the normal. And eventually what you'll have is, as it bends further and further away, it's going to actually bounce so far away that it stays in the surface that you were, or inside the object that you were originally trying to get out of. So we've got this angle here that bends the light this way. But as you get further from the normal over here, you're going to have the light that is, at one point it's going to bend it along the surface. This point is called the critical angle. And if you exceed the critical angle, flip the page, what you're going to have happen is this. Here's my barrier. Here Ni is greater than 1. Here Nr is equal to 1. This is our normal. Here's the light. This is theta C. One sec. I totally forgot about you. Yeah, at the 45-minute mark, if I still haven't come and talked to you, I definitely forgot about you. I'm sorry, Garrett. Next time, if I forget about you, stick your head around at the 10-minute mark, not the 45-minute mark. My apologies, Garrett. So at the critical angle, you're going to have light that passes along this way, right along the barrier. As you exceed that critical angle, you're going to have light that bounces back in, and it's not actually going to escape. It's going to stay within, I'm sorry, Garrett, the medium that you were in. You were supposed to write that test a month ago. That's okay. So the light will stay inside. And this is the cool effect called total internal reflection. It only occurs when light is passing from a medium with a lower index, into a medium with a lower refractive index. And so the example that I gave you before looked like this. When I gave, I'm gonna go low. So when I shine my laser right along this line, it goes straight through and hits that far corner. As I start to bend it away, we get bending light, bending light, bending light. You can see over here, you get this effect where the light is trying to leave, but it bounces off the boundary here and hits this bottom edge and comes out and hits me in the chest. So this right here, no, now it's going out to Mr. Vries's class. Don't want that. This right here is an example of what we call total internal reflection, where you get the light coming in at such an angle that it bounces within the object. There are two rather fascinating applications of this. One of them, well, actually both of them cost a lot of money. One of them is in gemology, so gemstones. If this becomes your field of study, if gemology is what you're interested in, then this is something that you need to take advantage of. This is an example of a cut diamond. When you cut diamond, you will set the diamond, maybe it'll be in a ring, This will be metal. And what you will want to be able to do is design this thing such that light coming in the top bounces around inside for a while off of all of these internal angles and then comes straight back out the top. The better these diamonds are cut, the more brilliant they will shine. Now, I hope none of you have done this because you're all far too young. But should you go engagement ring shopping, the diamonds that are larger and cut better, obviously they're going to be more expensive. But next time you're at the mall, fake it. Go in there with someone, pretend that you're looking for an expensive diamond, and you'll see this effect. You can tell what diamonds are cut well versus diamonds that are not. Because you'll get this on a diamond that's that's cut quite correctly. You'll get this light coming in the top, bouncing around everywhere, amplifying the light that you see coming out the other end. And you get this brilliant, brilliant shine. A diamond that's cut, or any gemstone, but a diamond is the best example. A diamond that's cut poorly, if you put it inside the setting, I don't know whether this is yellow gold, silver, rose gold, if you cut it such that the bottom isn't at the right angle, you'll have light that bleeds out that bottom end. It'll reflect off the metal that's underneath, and then what you'll have shining through isn't just pure white light. You'll start to get the reflection off the metal under the diamond. And instead of getting clean light, like you would off of a correctly cut gem, it's going to start to look muddy. And muddier depending on the color of the metal underneath. Yes, you look at you're about to put up your hand. So if you've got yellow gold under here, you're going to start to see that yellow coming through the diamond. It's going to wash out the brilliance of that diamond. This is one application of this. Another application of total internal reflection is in something called fiber optics. Do any of you know anything about how fiber optic cables work? Okay, has anyone seen a fiber optic cable? Like the inside of a fiber optic cable? Here today you say you have. What does it look like? Okay, fiber optic cables suck to break. Other cables don't. Like if you have like my network cable on the ground there, that's just a regular copper wire. If I were to take a pair of scissors, cut the wire, I could get some more copper, complete the circuit, tape it up, and I would have a functioning cable again. Fiber optic is a little different. How a fiber optic cable works is you get a cable from a cut end, looks like this, and then on the inside you have a bunch of these on the inside, bunch of little cables on the inside, and each one of these are glass tubes. This is why cutting a fiber optic cable sucks. Because if you cut a fiber optic cable, now all of a sudden you're shattering all this glass. It is not easy to repair broken glass. And you're doing it to all of these little tubes. These little tubes are flexible, which means they're really, really thin. There's a whole bunch of them packed in, which is, if you guys have seen the news and people complaining about Russia and China damaging cables, China between the mainland and Taiwan, and Russia damaging cables in the ocean connecting Europe to either Scandinavia, the UK, or North America. These are the cables that are lying on the bottom of the ocean floor, these fiber optic cables. And how a single one of these glass tubes work is like this. You get these tubes, and they're so thin that you can actually flex them. And if you shine a light at the critical or beyond the critical angle, you get this bouncing all the way through, and you get data transmission. The reason why this is so fast is you get data transmission literally at the speed of light. Now, computers, does anyone know the base language for a computer? What is the fundamental language for all computing? Starts with a B, meaning binary. Here today, what's binary? Zeros and ones. In binary, in computing's most fundamental language, everything is communicated in binary. Binary is 0 and 1. That's all it is. And combinations of zeros and ones. Now, it's really, really easy to convert anything that's a two system like this. It's either a 0 or it's a 1. Those are your only options. It's really easy to communicate that with light. Because a 0 in light could just mean the light is off. And you turn the light on for a sec, you get a 1. So to communicate in binary using light, all you have to do is send pulses of light either on or off at given time intervals. And now all of a sudden you're able to transmit computing information at the speed of light across great distances. Decreases, you know, have any gamers in the room? What does this decrease? Starts with an L. The time it takes to communicate over great distances. Latency. You can decrease latency this way, which is why the advent of like Telus' big fiber optic, we're laying cables everywhere internet, or you want to game with someone in Japan or in Europe, now all of a sudden, because the community, if you're on a fiber optic network, all of a sudden the latency is minuscule compared to the dial-up I grew up playing online games with. Because you can take advantage of this concept of total internal reflection. And this idea that past a critical angle, the light won't leave the wire. And you can connect people via fiber optic computer cables around the world and reduce latency to milliseconds instead of seconds, which is significant. It's pretty cool. When you're ready, flip the page. Let's do some math. There was a guy, a bit of a math aside, who developed a relationship between the angle things were bouncing in at, the angle that they were bending at, and these various indices of refraction. This is going to lead to something called Snell's law. So to lead to Snell's law, let's do a bit of review here. This is similar to scale factor stuff that I'm currently doing with my nines. This is the kind of stuff that you need to be comfortably able to solve. How would I solve something like this? If I wanted to get x by itself, what would I do? Yeah, I want to get x by itself. I'm currently dividing by 12. So I'm going to multiply both sides by 12. It's going to cancel there. How do I multiply that whole number by that fraction? Yeah, 12 over 1, and then I apply numerators and denominators. So what I'm going to get here is that x is going to equal 12 times 17 over 1 times 8. And this is going to be 25 and a half. I'll just tell you what that value is. If I wanted to solve something like this, there's two ways to do it. What are the two ways to do it? There's two options, either this option or this option. Ugh, I hate cross multiplication. As a math teacher, I hate cross multiplication. What do you mean by cross multiplication? Yeah, what we're trying to do is get the x out of the denominator. So we're going to multiply both sides by x times x times x. And I'm going to get rid of this denominator. So I'm going to multiply both sides by 4. On the left-hand side, those x's are going to cancel. The 4's are going to cancel. On the right-hand side, the x's are going to cancel. And yes, here today, we have now proven why cross multiplication is a thing. As a math teacher, I hate cross multiplication because students learn it in middle school and then they forget how to use it properly. So this is going to give me 6x equals 5 times 4. Then to get the x by itself, I need to do what? How do I get the x alone? Yeah, I divide both sides by 6. And so we're going to get that x is going to equal 20 over 6, which is equal to 3 1/3. That's not the only way to solve this. Instead of cross multiplying, There's another technique that we can employ instead. I like it better. It's easier. Does anyone know what it is? When what you have on the left and the right are both fractions. If I have 6 over 4 equals 5 over x, a really easy way to deal with this is to reciprocate. What's a reciprocal? Do you remember in math? You flip the fraction. The numerator becomes the denominator becomes the numerator. As long as you do it to both sides, that's a totally valid mathematical operation. Instead of 6 over 4 equals 5 over x, you can get 4 over 6 equals x over 5. And now all you have to do is multiply both sides by 5 and you're done. You're still going to get x equals 20 over 6, which is 3 1/3. And you can get away from this messiness that is cross multiplication. Take the reciprocal of both sides and then multiply by your new denominator. One skill we're going to need. Here's another one. We don't need all of trig, we just need sine. So sine is a trigonometric function, which by this point you should have all seen either in math in grade 10, or if there was no snow and your math teacher managed to teach it to you, you saw it in grade 10. Or Liam, I'm sorry, you had to wait till Mr. Myers taught it to you in grade 11. Which he just did, yeah? Perfect. We're going to use it again. But it's just sine. It's easier. So if I took the sine, if I wanted the sine of 32, this is just something you ram through your calculator. The sine of 32, you take your calculator. Sine is sine. I'm going to put 32 in there. We're going to close the brackets. We're going to hit equals, and you're going to get a value, 0 point, whatever that is. 529919642. We'll round that to 2 decimal places, and we'll call that 0.53. The only thing that matters is that your calculator is in what mode? You need to be in degree mode. Gernavin, I always forget. You're not in math this semester? It's next semester you're in IB? Okay. Then never mind, this won't matter. None of you are in math right now, math 12 or IB right now? Sorry? Thank God she says. Okay, good. Calculators can function in multiple modes. You can be in either degrees or radians. You'll learn about radians in pre-calc 12 or in IB, so this shouldn't be a problem for any of you. These you just ram through your calculator. If I want to do something like this, how would I solve for theta? What operation would I use here today? Sine -1, or also called sine inverse, also called arc sine. There's a lot of different language to it, depending on who's teaching it to you. But yeah, you use the opposite operation on the other side. So here then, theta is going to equal the sine inverse of 0.14. This is going to give you the angle now. And so if I ram this thing through my calculator, I'm going to use shift, I'm going to push sine to give me sine inverse, and it was sine inverse of 0.14. We close the angle, equal, or close the brackets, and this is going to equal 8.047, which I'll round to 8.05. So theta in this case is going to equal 8.05 degrees. Now all of a sudden we've got a measure for an angle. How do we feel about this? All of you are like, yeah, I can totally do this. I either just saw it or I saw it in grade 10 and I'm comfortable with it. Yeah, you're good with this stuff. Diego, you're good with this stuff. Bob, yes? Bobby, we're comfortable with trig? Cool, because it's wildly important for Snell's law. Let's put it all together. What we're going to start having is fractions that have sine built inside. It's going to be great. And what we're going to start solving for are either value, like just x's outside of a sine, or a theta buried within. And so I'll just demonstrate 2 of these and I'll show you Snell's law. If I wanted to solve this thing for x, as Hirde said before, we could cross multiply, or as I demonstrated, we can reciprocate. I don't particularly care how we do this. How do you guys want me to do this one? Hirde wants cross multiplication. Okay, if I cross multiply, what I'm going to get is I'm going to multiply both sides by x, and I'm going to multiply both sides by the sine of 15. What that's going to give me is that x times the sine of 60 is going to equal 1.3 times the sine of 15. This thing, sine 15, multiplies up as a single mathematical object. Then to get x by itself, I'm just going to divide by the sine of 60 on both sides. Oh, that's horrendous. Because now you're introducing rounding error. Because the sine of 15 and the sine of 60 aren't going to be clean. I mean, sine 60 is, I mean, you could. If these were clean angles, like this 60 is a special angle, you could convert it into, have you seen that already? Root 3, root 2, 1 over root 2, whatever they are. Okay, you've seen that? You could theoretically do this, but because sine 15 isn't one, I wouldn't. I would get as much as you can into the habit of leaving it as sine of whatever the angle is, because now we can just pull out our calculator. We don't have to deal with any rounding error, and this is just going to be 1.3 times the sine of 15, close that bracket, divided by the sine of 60, close that bracket, and the only rounding you have to do is at the end. And in fact, there's a few special angles in there because we get something that looks like that, which is gross. I want that. And so this is going to be x is going to be equal to 0.39. Again, I'm going to round it to 2 decimal places. But that's a really nice result. I like that a lot. But that's the number that's going to be more useful. If I'll demonstrate the other method on this top one here. If instead we're looking for theta, to make my life easier, does it matter? Sure, we can cross multiply here. Sine 40 times 1 isn't going to change anything, and this is going to equal 1.5 times the sine of theta. Now to get theta by itself, the first thing we're going to do is what? No, what? Sorry? Yes, divide 1.5. So here the 1.5s are going to cancel, and you're going to get sine theta. It's going to equal to sine 40 over 1.5. Now, how do I get theta by itself? Yeah, I take the sine inverse or negative sine. So what I'm going to do here is I'm going to take the sine inverse of this whole piece, and that's going to get rid of this. So we're going to get theta is equal to the sine inverse of sine 40 over 1.5. And it's going to look like this on your calculator. You're going to have the sine inverse. It's going to open a bracket of sine 40, close this first bracket, and divide that result by 1.5 and close that bracket. And you're going to get this, an angle measure of 25.37 degrees. Questions, comments, concerns about anything I've just done? Okay, if you have no questions, flip the page, and I will show you why this is useful. Because of Snell's law. Snell's law was named for this fantastic gentleman here, Willebrord Snellius, which is an awesome name, and he was a Dutch astronomer. Why would astronomers care at all about how light travels between mediums? Yeah, telescopes. Telescopes are kind of a huge deal. The guys who did the most work in optics at the birth of optics were astronomers. People who were trying to use it to see really, really far away. And what he discovered was that for a boundary between two media, the relationship, oh boy, I spelled that poorly.
relationship for an oh boy, come on, read off. An incident and refracted wave is given by the following relationship. He discovered that if you take, for this situation, where you have a boundary between two media, there's our medium, or there's our normal to the medium. If light is coming in with a particular angle of incidence, and it gets refracted, there's our theta r, inside a new medium, where you've got an incident index of refraction and a refracted index of refraction, the relationship is going to go like this. The sine of theta I divided by the sine of theta r, so the sine of that angle, divided by the sine of that angle, is going to be equal to nr, the refracted index, divided by ni, the incident index. Interestingly enough, this is also equal to the speed of the wave incidentally divided by the speed of the wave refracted, which is also equal to the wavelength of the light incident divided by the wavelength of the light refracted. Where VI and lambda I are up here, they refer to the light coming in, and VR and lambda R refer to the refracted light down here at the bottom. Now, because we have 4 ratios and they're all equal to each other, you can use, depending on the question that you're given, you can use any 2 sets of fractions here to find whatever piece of information you're looking for. Snell's law at its most fundamental is actually these 2. At its most basic, he started with these 2. And it can be reworded as, we're going to multiply the ni up, we're going to multiply the sine theta r up, and you're going to get this. Ni sine theta I is going to equal nr times the sine of theta r. And this, of course, shows up on your formula sheet here and here. These 2. And I think for the sake of time, I think I only have 5 minutes left. We're going to leave this right here. Tomorrow will be our last full lesson. I will show you Snell's law and refraction, and we will be done. Physics 11 for fall 2024. Which is sad, because there's some really cool stuff coming. Shadows and images, lenses are really cool. If I had 1 more week, man, and I'll get it semester 2. Semester 1 is a week shorter than semester 1. Sorry, semester 1 is a week shorter than semester 2. I will finish this course next semester. Okay, yeah, you guys can pack up. You have no homework from me. We're going to finish Snell's law tomorrow. We'll look at refraction, and then we will be done.